Hello everyone. So if you are watching this video, you are about to take the notes for Unit 2D Day 4. We just kind of are trying to consolidate a little time here, and I figured that this is a nice set of notes that I think can be done from home with a video to go along with it. And the reason I think that is because a lot of these ideas are things that we've looked at before in our course, and some like specific inverse ideas that are they're special for logarithms and exponents. So we decided to make a day 4 notes a couple years ago to kind of like wrap this up, but also connect it to some ideas from our previous units on inverses. So um, aiming to only take about 10-15 minutes of your time with this video. So without wasting any more time, we'll get started. If you need to pause right now, so uh, turn over to the page that says Day 4 Notes. And I'm actually looking at the packet right now. And this can be found after the applications problems. So after the notes, you are going to be page 17. So this is the very end of the packet, page 17. So all right, so let's get started. It says that note that a logarithmic function g of x, so you see there's a little log base b of x, is the inverse of an exponential function f of x, b to the x. So they want us to use properties of inverse functions and logarithms so that we can verify that these are inverses using composition. So if you remember last time we talked about inverse, we know that to figure out if things are inverses, right, to determine or verify, we have to take one of the functions, plug it into the other. If that equals x, then we're going to also take this function, put it inside, and if that ends up equaling x, then we know that those two are inverses. This is also very trippy because there's two versions of me right now. So let me see, can I just turn that off? Okay, there we go. Yeah, that was freaking me out. So, all right, so let's get started. We're gonna take f and we gotta plug it into g. So f is the exponential function, and we're going to be plugging that into g of x. So I'm just gonna write log base b, but instead of x, I'm going to be substituting in the function f, which is b to the x. So now I'm looking at this and I'm thinking, all right, well, a logarithm is really just a missing exponent. So the way that we need to think of this is that it's asking us b to the what equals b to the x. So we've got to fill in that box. This is just equal to x. Okay, so hey, we've verified one direction. So now we've got to take g of x, the logarithm, and we're going to substitute it into the inverse f of x. So I'm going to write down b, and instead of this little x, right, I have to write g of x, and that is log base b of x. Now, this looks very strange, right? We have a base, and then it's raised up to an exponent that is a logarithm. So it's a little bit strange, but this is going to be one of those that you come to recognize as undoing. Just as we take x squared, and you take the square root and it ends up being x, or you could square, right, a square root and become x. Well, b to the log base b, that's equal to x. So this little base b with a log and that big base B can almost be viewed as canceling each other out. Now that's not mathematically what's happening, right? There's a little bit more inverse work under the hood there, but in terms of our understanding and kind of like what we want to commit to memory is that if we see this base B and then a logarithm of the same base, we know that this just simplifies down to x. So it's a little bit like, oh, it's magic right now, but that really is the true undo button for an exponent or a log. So both of them ended up being x, so we can say, right, f of g equals x, which also equals g of f. So they are inverses. inverses. So, and of course, if you need to pause and recopy any of that, you can do that. We're going to move on to the next example that asks us to verify that log base 7 of x and 7 to the x power are inverses. So to verify inverses, we're trying to prove that f of g equals x, and then we're also trying to prove that g of f equals x. So we're going to look to do that here. Let's see, f of g is equal to log base 7 of 7 to the x. So you can see that I took g of x and put it right in there. And here we go. We see that base 7 and then raised 7 to the x power. So that does equal x. So we can say, all right, f of g equals x. And then we'll go over here and say g of f. And instead of the exponent being a little x, the exponent is going to be log base 7 of x. And we talked about, actually, right here next door, that this does equal x because the 7 and the log base 7 sort of work as opposing forces there, just as square root of x squared cancels to x. All right? So those are just kind of two basic examples for, just kind of proving that logarithm and exponents are very much so related, and the fact that they undo each other. So when I get to these examples, I scratch my head a little bit because to me, I see example 2 or whatever these examples are. I see these as almost like downgrades of what we just did above, right? Because this isn't even an equation. This is an expression. So we've got 10 raised to the log base 10 of 2. So we have one of these scenarios where we have 10 being raised to a base 10. So this ends up actually just equaling 2. So you can view these as almost like canceling each other out. Now over here is a little bit different of a story, right? Because now we have a base of 3, but then we have inside of the argument is a 9 to the x. So when I'm proposed one of these questions, I like to just kind of like create. Here's the base, and I know that we're always wondering like what is it equal to, right? So 3 to something equals 9 to the x. So here I'm using the definition of a logarithm. I'm changing it into an exponential equation. And now I'm going to use one of those strategies we learned in day 2, where I'm going to rewrite that 9 as 3 squared to the x. So now it follows that we have 3 to the something equals 3 to the 2x. And now we know what that box is, right? That's right there. So this is all equal to 2x. Okay. Number 3 is easy like number 1. The log base 7s cancel out with the 7. And sorry, I got to stand back so I can see what that is. It's honestly just equal to 4x. Awkward, strange, but we're moving on. They cancel each other out. So now 4 is very much like 2, where those bases are not identical. So it's best to rewrite using the definition of logarithm and exponent. So I see 125 to the x. So I'll give you a second. Pause, try to think of how to write 125 with a base of 5. Think about that for a second. And what would we have? Go ahead, say it out loud. 125 is what as a power of 5? Good job. You got it. 5 cubed. So if I want to know how would I fill this box, I would fill that box with 3 to the x, because we would have 5 to the what equals 5 to the 3x. So the answer to what is 3x. So number 1 is 2, number 2 is 2x, number 3 is 4x, and number 4 is 3x. So that does it for page 1. And I'd like to just kind of go for it, because you guys can go back as whenever you need to. Like pause, rewind, whatever. So I'm on page 2, and this should be a little bit of a blast from the past, because it says finding inverse functions. Right? So it says when given a function, we can find its inverse using the general steps below. So you're going to recognize a few of these in step 1 and 2, and then it changes a little with the logarithm. It says interchange the roles of the input and the output variables. Right? So that's going to be us swapping x and y. Then it tells us to isolate the logarithm or the exponential by performing inverse operations as necessary. And then step 3 says to rewrite the expression using the definition. Oh man, I just highlighted everything. No point in highlighting if you highlight everything. But anyways, at that moment, right, there's going to be a form switch. So if you started in exponent land, you're going to end in logarithm land. If you started in logarithm land, your final destination is exponent land. Right? Because if I give you an exponential expression, and I said, equation, exponential equation, what's the inverse equation? Well, if you were given an exponential, chances are the opposite is a logarithm. If you're given a logarithm, right, a logarithmic equation, the inverse has to be an exponent or an exponential equation. So that opposite stuff is going to happen throughout this whole thing. So as I look across these examples, right, I see example 1, 2, 3, and 4. They all have logarithms. So before I even do anything, I know that the answer to 1, 2, 3, and 4, what is the inverse? The inverse is going to contain some kind of exponential equation, right? When I look at number 1, I just look at the base and I see 3. So that tells me that the exponential equation, right, the inverse is going to be 3 to the x, or 3 something power. With number 2, you see a base 5. So you're thinking, okay, it's going to be 5 to the something, and there's going to be a couple pieces floating around. When you look at number 3, you see a base 4, but it's a logarithm. So the inverse is going to be 4 to the x with some stuff around it. And then with number 4, again, you have log base 6. So it's going to be 6 to the something with some stuff happening on the outsides. Okay, so it's our job to figure out all those details, all those what's around it questions. So we're going to try this. Right? We're going to swap x and y here. X equals log base 3 of y. And it's our job to get that y isolated. So the only way that we can do that is to change, right? And we need to change this into an exponential. So the base is 3. The exponent was the answer to the logarithm, which is x. And the answer is y. So the inverse to the log base 3 is 3 to the x. And step 4, please just change that back into inverse notation now. So, oops, sorry, not f. I just looked at the equation originally, and the original equation is a y equals. So we're just going to say y inverse equals 3 to the x. So I like to match whatever I was given. So in number 2, we were given f of x, so we'll say f inverse of x there. But for our purposes right now, for number 2, we're going to set x equal to the log base 5, and we're going to put y minus 2 inside. So this logarithm is already totally isolated. There's nothing being added on the outside. There's nothing being multiplied. So we're just going to go right into the exponential now. Okay, so put it into exponential form. The answer is going to be y minus 2. And the base is 5, the exponent was x. So now I have y minus 2 equals 5 to the x. I need to get y all by itself, so I'm going to add 2. And we have f inverse of x equals 5 to the x plus 2. So the thing I like about these is that, just as with parabolas, cubics, square roots, Right? We can look at the original function. We see a 2 on the inside, and it's being subtracted, right? So all of a sudden, you compare this 2 on the inside subtracted. Now it's a 2 on the outside, and it's being added. So not only do we have the opposite location, but we have the opposite operation. And that's another mental check to see if we did these correctly. So in number 3, we've got x equals log base 4 of y minus 2. And right now, the logarithm is not isolated, right? So what part of the logarithm needs to disappear? You got it. It's the minus 2. So we've got to add 2 to both sides. We get x plus 2 equals log base 4 of y. And now the logarithm is isolated. So we're going to go into exponential form, where this is the exponent. So 4 to the x plus 2 equals y. And looking at the original, it was f of x. So we're going to say f inverse of x equals 4 to the x plus 2. And sure enough, we had a minus 2 on the outside before. Now we've got a plus 2 on the inside. And when I say inside, I mean right up here in the exponent. Okay, so inside for an exponential is the actual exponent, and the outside is whatever's happening afterwards. All right. I know this is rapid fire, so you can pause at any time if you need to. Okay, with this one, I'm swapping x and y. So I've got x equals log base 6 of y minus 1 plus 9. And let me show you the shortcut on this one. Right? Mentally, you know this is base 6. So we're going to say y inverse equals, it's a 6. Now, this was a minus 1 on the inside and a plus 9 on the outside. So if there was a plus 9 on the outside, there's going to be a minus 9 on the inside. And if there was a plus 1 on the inside, now it's a plus 1 on the outside. And that is the answer there. If you don't follow what I did there, it's really just saying, okay, subtract this 9 away. And now you have x minus 9 equals log base 6 of y minus 1. Rewrite as a logarithm, 6 to the x minus 9 equals y minus 1. And then you add 1. And then that's exactly where we get. So again, number 4, you could do it a short way, do it in your head. But that's the process that we would outline and go through to get the inverse. Okay, a couple more here. We have swappage happening. X equals 4 to the y. Look back here. Plus 1. So this time we're worried about the exponential being isolated. So it is isolated. I have an answer. I have an exponent and a base. So I'm going to rewrite as log base 4 of, log base 4 of x equals y plus 1. Remember that a logarithm is an exponent. So if you're looking for, well, what's the piece that goes on the outside, it's the exponent now. Remember, we have answer equals base to an exponent. So it goes log of base of the answer equals that exponent. So we're almost there with this one. Minus 1, and we get y inverse equals log base 4 of x and all minus 1. So that was our first one where we went from exponential to logarithmic. Okay, almost there. x equals 5 to the y minus 3 plus 2. So you kind of look there and you say, okay, swap the x's, swap the y's. Now what? Yeah, good. Yeah, minus 2. So x minus 2 equals 5 to the y minus 3. And now we've got an isolated exponential. Exponent. Okay, so that's the exponent. We're going to have y minus 3 equals, and we've got log base 5 of x minus 2. And we have to add that 3 to isolate the y completely. So we have, whoop, that's not a y, that was originally an f of x, right? So let's write that properly. F inverse of x equals log base 5 of x minus 2 plus 3. And going back up to the top there, right, plus 3, because there was a minus 3 on the exponent. When we look for the minus 2, it's because there was a plus 2 on the outside. So that looks good to me. And we have one more. And this one's a little bit of a doozy, so I'm going to need a little extra room here. The reason I say it's a doozy, we just have that like multiplier of a 3 on the outside, so it's going to look a little different. Right? So just remember we have to isolate the logarithm first. So x equals 3 times the log base 2 of y plus 5 all plus 7. So I think that this won't be too bad, but we have to isolate the logarithm correctly. So we can't quite divide the 3 out yet. We gotta subtract 7 first. We need to work our way outside in with these. Base 2. Now we can divide by 3. So we're going to divide the whole thing by 3. Oh well. So the 3's are gone. Now I have log base 2 of y plus 5 is all equal to x minus 7 over 3. So we've reached the stage in our journey when, wow, we have a base, we have the answer, and we have an exponent. So I'm going to write 2 to the x minus 7 over 3. So let's see. I've got the base, I've got the exponent, and it's equal to y plus 5. Subtract 5. We end up with y equals 2 to the x minus 7 over 3 minus 5 equals y. And the only thing I would change there, oh, sorry, y equals both times. The only thing I change there is the notation. We have to have an inverse. Inverse notation. So there's the dividing by 3, there's the minus 7, and there's the minus 5. That's compared to the plus 7, plus 5, and times 3. So that would be the inverse for number 7. And thank you for your attention here. And it looks like I just recorded this for about half an hour. So hopefully it still loads. Pretty please. And just take these notes, and we will do the practice together in class when I see you next time. Have a good one. Oh, okay, under 25 minutes. I wish I had done a little less. Sorry.